All right, friends. So today we are going to learn how to solve a system of equations using substitution. So generally, we first learn how to solve a system by graphing. So we'll do a little refresher of that here. When we're solving a system of equations in general, we're trying to find the ordered pair that will make both equations true. Or if it's three equations, that would make all three of them true. If the variables are not x and y, it wouldn't be an ordered pair, right? Like a and b or r and s or whatever we're talking about. But in this case, right, with the graph, we want the ordered pair that's going to make both equations true, right? So we start with the y-intercept, right, which is -3. My slope's -1/2, so I'm going to go down 1 and 2 to the right. I can go up 1 and 2 to the left. Right, eventually we will want to connect our points here with our straight edge. We're going to want to use arrows. We're going to want to label. Right, so that's y equals -12x minus 3. And we're going to see where that's going to intersect with our second line, right? So my y-intercept is up here at 2. My slope is -3 divided by 1. So we're going to go down 3 and 1 to the right. And it looks like I've got my point of intersection, but I might as well continue my line in the other direction. We're going to, of course, be thorough here. We're going to connect our points. We're going to use arrows. We're going to label. All right, and we're going to, maybe we want to circle this, right? But really, we're going to want to write a sentence. And we're going to want to do that pretty much with all of our systems, right? The solution is, and it looks like that's going to be 2, -4, right? But we don't know if that's right. We don't know if we graphed it wrong. We don't know if we found the wrong point. So we can check both of our equations, right? So if I want to take a look at my first one and my second one, right, in both cases, I'm going to want to substitute 2 for x and -4 for y. And if both of them check, then we know we correctly solved this system, right? Right here, I've got -1/2 of 2, which is -1, and -1 minus 3, which is -4. So far, so good. And here we have -3 times 2, which is -6, and -6 plus 2 is -4. So definitively, we know that we solved the system correctly. So a little refresher there on solving systems graphically, right? Now, obviously, that's not the most efficient way, right? So if I'm looking at something like this, well, for one, I don't have slope-intercept form. For two, if I'm using intercepts, let's say for the second one, my x-intercept is going to be 21. I may not have x or y intercepts that are integers, and then how would we graph it? Also, we would need a graph, and that's not super efficient if my answers are fractional, if they're big, small, right? So we want to have other methods, right? So we essentially have the substitution method, and then we have our elimination methods, right? Now, the substitution method I'm really only going to use if I have one of the equations in the form x equals or y equals. Because in those cases, I know that I can simply replace that variable for the other expression in the other equation. So let's see what that means, right? So x is equal to y plus 5, right? So we don't have a numerical value of x. We know what x is equal to in terms of y. So wherever I see x, right, I can literally replace it with y plus 5. Now, everything else, every symbol, every number, every variable term, whatever you want to call it, everything else stays exactly the same. So now we have a pretty simple equation with like terms. Right, so we add the like terms, giving us a two-step equation, and we should be able to solve this pretty easily. Right, we should get y is equal to 4. And then we need to solve for x, right? So this is not checking, right? A lot of times my students still, when I ask them to check, they'll be like, oh, well, I checked when I solved for the other variable, right? This is not checking, right? This is finishing up with solving the system, right? So I get x is equal to 9. And we'll say then that the solution, right, we think, right, the solution is going to be 9, 4. Okay? I didn't check anything yet, right? I could have got 17, -3, right? Just because I take whatever crazy value I get for x or y and then sub it in to find the other one, that's not a check. So if I did want to check this, right, we're going to do exactly what we did with the last one. I don't think I need to check every one, right? In other words, I'm just kind of showing you the procedure of what we would do for the check. Right, but checking is not what I did in the red and the orange. Checking is what I'm doing here, right? So I'm going to substitute 9 for x and 4 for y. right? And technically, I guess they should both be in parentheses for consistency's sake, right? In both equations. We want to make sure that they both work. So obviously the first one's going to check pretty easily, right? 9 is equal to 9, right? And this one's going to check almost as easily, right? So 9 plus 12 is equal to 21. Fantastic. So we did this correctly, right? Now, if you're the type of person that needs to take some notes here, these are going to be our guidelines for any sort of substitution, right? We're going to substitute the value of a variable in one equation into the other. And again, I'm really going to lean on this method if I've got x equals or y equals, right? So if I have something like this, right, that's probably not the best method. You know, I could solve for x in the first one. I'd say x is equal to negative 2/3 y plus 10/3, and I can substitute that in the other equation. Not going to be super efficient. Distribute if necessary. So that's going to be kind of the back end to the lesson here. Solve for the remaining variable and check. So the same things that we just did there. So I'm going to be consistent, right? If I know what y is equal to, I'm going to replace y. Now again, every term, every other sign, every symbol, everything else is going to remain exactly the same. So we can imagine what would happen if instead of plus y, that was minus y. So we'll see that a little bit later, right? Certainly we've got some like terms here. And again, we get a pretty basic two-step equation, right? So I see that 7x is negative 14, right? So we get x is negative 2. All right, we're halfway there, excluding the check, of course. So I'm going to go back to my original equation. Now, the question always becomes, right, which one do we want to substitute? Well, in general, it's going to be whatever's easiest for you. Could I substitute negative 2 into the second one, right? Yeah. 2 times negative 2 is negative 4. Add 4 on both sides, y is negative 9. Right? I could do that, but it's going to usually be easier to solve for the other variable with the y equals or the x equals, right? The equation that's solved in terms of that variable. Right? So again, I would also get, if I did it the other way, like I kind of dictated there, negative 9. And then our solution here, right, we're going to write it as an ordered pair. Negative 2, negative 9. Now, if it was any other letters, right, that's not explicitly going to be an ordered pair, right? If there was a equals, 5b plus 1, you're not necessarily going to write it as a comma b, right? You're going to write it as a equals negative 2, b equals negative 9. So this is one that's kind of deceptively simple, right? When it teaches us, and this is always the one that for some reason will stump kids, right? Because they're not used to both of them being kind of like in slope-intercept form. Now, there's an easier way that I like to think about this, right? Like if a, right, I'm going to say y is like a, right? If a is equal to b and a is equal to c, right? If I'm given those two statements, then hopefully I can deduce that b is going to be equal to c. Right? Because if b is equal to a and c is equal to a, then they're equal to each other. Now, sometimes that kind of clicks and sometimes it doesn't. So if that doesn't click, right, we call that setting equations equal to each other. And if that doesn't click, I'm going to say, well, I'm going to replace the second y with what the first y is equal to, or vice versa. Right? Which is then going to look like this. And this should be pretty easy, right? I'm going to do both of these in one step. I'm going to assume that we can handle that. Right, so I get 3x is equal to 6, so x is 2. And both of these would make solving for y pretty easily. I'm probably going to defer to the second one, right? Because if y is equal to 7 minus x, when x is equal to 2, right, y is equal to 5. Right, now we've got our ordered pair. That's going to represent our solution, and that's going to be 2 comma 5. All right, so here's one where maybe we want to use substitution, maybe we don't. Right now, if substitution is like the only tool in our toolbox, then we're gonna be okay using it, right? If not, would we want to use elimination? Well, if you know how to use elimination, elimination is really geared towards standard form, right? Like both variable terms on one side, usually the left, and then the constant on the other. Now, it doesn't have to be like that. So this one's kind of nebulous, right? Kind of in the middle. Well, probably what I would do is I would figure out how I can solve one of these equations for x, right? Because both of the y terms have coefficients that are not 1. So if I want to solve the first equation for x, I'm going to just move the 3y. And we move terms, right, algebraically by adding its opposite on both sides. So what I'm going to get is x is equal to 3 minus 3y, right? Because what's going to happen? This 3y and negative 3y will eliminate. X is equal to 3 minus 3y. Now I can go ahead and say, well, if this x is equal to 3 minus 3y, right, and I can replace it. Now, could I have done the same thing with the second equation? Sure. right? Since x plus y is equal to 4y, if I add negative 4 on both sides, I would get x is equal to 4y minus 4, and I would sub that back in for x in the first equation, okay? But I think this should be easy enough, right? We've got some like terms here, right? So I've got negative 3y plus 7 is equal to 4y. This one's pretty easy. Looks like we're going to get y is 1. Right? So if y is equal to 1, doesn't really matter which equation I use. I'll go with the second one just for the sake of it. X plus 4 equals 4y, right? I would say the same level of difficulty for both of these. I don't really see a tremendous difference in one versus the other, but again, you're more than welcome to use whichever one you feel is going to make life easier for you. All right, so we get x is equal to 0. All right, now remember, 0 is a solution, right? 0 is a number. It's not a positive number or a negative number. It's an even number, but it's not like no solution, right? So for example, right, if we had something like 3x, just as an aside, 3x plus 2y equals 5, 3x plus 2y equals 7, that's going to be no solution, right? Because I can't solve this thing. No matter what I do, 3x plus 2y can't be equal to 5 and 7 at the same time. So sometimes once we learn about no solution, anytime we see 0, we jump right to no solution. But our solution is here, it's 0, 1. And I can clearly see that if x is equal to 0 and y is equal to 1, then 3 plus 0 is 3. And if x is equal to 0 and y is equal to 1, then 0 plus 4 is equal to 4. So it checks pretty easily. All right, here's our two-step elimination, right? So when I gave you those 4 rules, right, one of them was distribute if necessary, right? So now y is equal to 3x, except the y has a coefficient. Now this should not make things significantly more difficult, right? So the only thing I'm going to do here is I'm going to say, well, we could do this in a few different ways. Let me start there, right? In other words, the traditional way is to straight up substitute, right? So that's why I said before, everything else remains the same. So what I wrote in red is exactly the same as what's in red in the original equation. The only difference is I replace y with 3x in parentheses. Now sometimes we kind of front run this a little bit. I'm going to say, well, what if I want to know what 4y is? Well, if I know that y is equal to 3x, then 4y is equal to 12x. And we're going to get the same thing here anyway, right? Because when I distribute the 4, I'm going to get the 12x. So it becomes a matter of preference. Do you want to distribute, because there's some problems where they'll give you, right? They'll say 4y is equal to something. And then sometimes we divide by 4 and then redistribute. And then it's kind of silly. Anyway, so we have 14x equals 28. Right, so we get x is equal to 2. And of course, I'm going to want to use the second equation, right? I mean, again, you could use the first one. Kind of a big waste of time, though. Right, so we get y is equal to 3 times 2. Y is equal to 6. Nice and easy, right? We've got 2 comma 6. Similar situation here, right? Except we have an extra constant. So again, this one is fairly similar to the next one. Right, I could use my front-running strategy still, and I'll show that on the side. So again, being consistent, right? Everything is exactly the same. The only difference is that y alone, not the 3, nothing else gets replaced. Alternatively, if you wanted to kind of front-run it, right? If I know that y is equal to 2x minus 1, then 3y is equal to 3 of those things, so 6x minus 3. And that's, of course, what we're going to get anyway, because here we now need to distribute. There's my 6x minus 3. We've got those like terms. That's 27. I was just kind of getting ahead of myself with the, so I'm going to add 3 here, right? So we can tell that 10x is equal to 30, right? So x is equal to 3. And again, we could use either equation. Certainly the second one is going to be significantly easier. Right, so y is equal to 2 times 3 minus 1. Y is equal to 5. And my solution as an ordered pair, right, should be 3, 5. All right, last thing we need to look at here, right, and you can say, well, that doesn't look that different than the last one, and that's true. But we do have a negative here, right? So that negative, of course, is going to have to be distributed, right? So 5x minus 2, and then in parentheses 3x minus 5. Now, could we use my strategy before about front running? We could. You'd have to be pretty careful. If you front run and you did 2y, it's not going to work. You're going to make a mistake. Let's say that. Right? You need to understand that that's not a subtraction sign, right? That's the sign of the 2, or the 2y, that is negative. So if I wanted to know what negative 2y is, I'd have to multiply that whole expression by negative 2. And that's what we should get anyway when we distribute, if we do this correctly, right? Because we know that this negative 2 has to be distributed, like always, right? So what's going to happen if we don't distribute negative 2? Well, the 6x will still be negative, but the 10 will be negative also. If we forget that that 2 is a negative 2, we're going to do 2 times negative 5 is negative 10. Our answer is going to have the wrong sign, and then our other variable is going to be completely wrong. So we combine the like terms at the front. We get negative x plus 10 equals 6. Right, so negative x is equal to negative 4. Of course, that means x is equal to positive 4. And again, we're going to do what's easiest for us. Right, so x is going to be 4. And so it looks like we're going to get y is equal to 7. Right, so my ordered pair here is going to be 4, 7. All right, so that's pretty much it as far as substitution. If you have substitution with 3 variables, you can kind of employ the same approaches there. You may need to just kind of, as a quick little aside here, right? So sometimes we'll see something like, just to come up with something simple, right? So I'm just coming up with this on the fly here. So what we should be able to do is we should be able to say, well, in my first equation, if I solve for b, I'm going to get b is equal to 10 minus a. And in my second equation, if I solve for c, I'm going to get c is equal to 16 minus a, right? I'm just adding negative a on both sides. So if b is equal to 10 minus a, and c is equal to 16 minus a, right? Now I'm going to get 26 minus 2a is equal to 12. I get negative 2a is equal to negative 14, and it looks like a is going to be equal to 7. And now I can just look at the first equation, and that tells me that b is equal to 3. I can look at the second equation, and that will tell, or the third equation, either way, it's going to tell me that c is equal to 9. So the substitution method is pretty powerful. Now, what happens if instead you had something like 2a plus 3b, 3a plus 4c, 5b minus 7c equals whatever? Well, now you're going to have to solve for those variables. So I could solve for the first one for a, I could solve the second one for a, the third one for b, whatever I want to do. Same thing as what I did here, right? You essentially want to get, maybe I'll make a video with 3 variables at one point, but the point is you can employ the same sort of strategies there, right? Like if I can solve this equation for b by moving 2a and dividing by 3, I can solve this one for c by moving 3a and dividing by 4. I can take those, and you may get some fractional coefficients, and you can sub it into that third, or in this case, it would be that equation there, and you can solve it. So I hope that you guys got something out of this. If you master substitution, next thing we're going to do is we're going to talk about using the elimination method.